Today, so until now we've been sort of working with. So what have we been doing so far? Sorry, exit. Until now we've been sort of working with countries random variables. So we had x is a so S was an uncountable set, for example, and x was a country random variable. And then this was characterized by a function which is f sub x, which is from r to 0 infinity, and it was piecewise continuous, and integral was 1. Right? So this is the PDF of x, and and the chance that x was in a set A was given by integral A f sub x. And A is an event space. And we also been trying to understand how to understand transformations of random variables. So suppose y was equal to some h of x, we decided how to find the distribution of y. We said we had 3 steps. One was calculate the distribution function of x. Function of x. And then from that, we said, okay, fine, we find the distribution function of y. And then from that, we find the density function of y by differentiating. That was the idea. So that's what we've been doing so far. Today we will start with a different topic. So today I'll try and do the same way like I did in discrete random variables. So I'll try and understand. This is 5.4. There's multiple continuous random variables. So when you have the same idea, then you have 2 or 3 random variables, you want to understand the dependency. So while analyzing 1 or 2, analyzing, let's say, 2 random variables, one may consider what's called the joint density. So that's analog to the joint PMF of discrete random variables. So it's analogous of the joint PMF, so joint probability mass function, or joint distribution, we can say, of discrete random variables. So here this is continuous, continuous random variables. So here of course, this can be generalized to n as well. So it will not be 2 is not the sort of can be generalized to n as well, like in the discrete case, n bigger than 2. But first we focus on 2. So the first result I'd like to sort of share with you, like what is the joint density? In the discrete case, let me come back to this. In the discrete case, we were able to say that okay, we have probability x equal to x and y equal to y. That gave us the joint distribution of x. So in the continuous case, one has to be a little bit understand how to phrase this joint density. So here's the first theorem. This theorem, theorem 1. Okay. So let f be a function from R2 to R, be non-negative. Function. So I'll assume f is piecewise continuous. In each variable, that is in both x coordinate and y coordinate, and for which the double integral is 1. Okay, the double integral is 1. fxy dx dy is 1. Then for any event a, so for any event a contained in R2, so event means I would take the Borel sets. That is the events that are generated from open intervals. For any event a, the probability of a, if I define the probability of a to be equal to the integral over a f of xy dx dy. So define p of a to be this, then p defines a probability. P is a probability of or not. And f is called density function. So the proof I will leave as x. So the idea is that in the same as the one-dimensional case, when we integrate f in the previous step, we said that probability of x in a was given by integral over a f sub x of x dx. In the same way, in the two variable case, we integrate a over f, you get a probability a on. So proof I'll leave as an exercise. It's the same as the one-dimensional case. So proof. I'll leave as exercise. And one can check it slowly. So the one way to define a probability in R2 is to sort of take a joint density of two variables, and which is non-negative and 1. So now, so this is one way of characterizing dependence of two random variables. So what you do is, so this is a definition, 5.4. A pair of random variables x comma y is said to have joint density f of x comma y if for every Borel set A contain R2, what you do is you check the probability of x comma y in an A is going to be given by integral over A f of x comma y. Right? That's the definition of a joint density. So as in the one variable case, so just one small comment, remark. Just a small comment. that this word Borel set, right? I have not defined it properly in this course, but it's just the so for our consideration, we can think of A to be nice regions. So A to be let's say minus infinity to A across minus infinity to B, A and B. So it's enough. So I won't do a general definition of Borel set in this class. And from this comes an interesting fact. From the joint density, the joint distribution function of x comma y f sub x comma y of a comma b is equal to probability of x less than equal to a and y less than equal to b. That's the joint distribution function of x and y. And that for a continuous random variable is just going to be introduced from minus infinity to a, minus infinity to b, f of x comma y, dx, dy dx. So because y is first, so I put dy. For all a and b. So this is how one would understand the distribution form. So I just typically want f of x and y are write as f of a comma b without the dependency on x and y. But you can use calculus to go from capital F to little f by differentiating in each variable and so on and so forth. And so this is sort of standard calculus runs apply. Standard calculus. So f to little f is standard calculus. So standard multivariate calculus. So that's how one would go from the joint density to the joint distribution function and vice versa. You can differentiate each variable and go from f to little f, as long as f was continuous and so on. So let me just quickly recap. So the idea was that come here. Go and it's there. Save it. Save it. Save it. Yeah, it's the same thing. Okay, let me go back. Okay, let's open it to work. Let's here. Yeah. So here the idea is the following, that you have a random variable x is uncountable, then we know that you can give it by a density function, and transformations of which can become from the distribution function of x and y, and then come to the density function of y. Now when you consider two random variables, then you need to understand the joint density of the two of them. So that's what characterizes the dependency between x and y. So what we do is you first say that, okay, if you have a two variable function which integrates to one and is non-negative and features continuous, then integrals over that function define probability. That's what the first theorem says. Then if you have a pair of random variables x and y, it's set of a joint density f of x and y. If for every Borel set, probability x and y and a is the integral over a f of x, y, dx, dy. And Borel sets are a little bit too general for this course, so I'll just think of them as rectangle, like minus infinity to A cross minus infinity to B as our generic sets. And from this comes an important definition called the joint distribution function of x and y. And these are the key to understanding dependency between two random variables, x and y. And multivariable calculus will tell you how to go from f to little f. Whereas, so now let me try and do some examples. So let's do a simple example. The first one of two random variables. Let's say example 5.4.3. So let's say take a rectangle R. Let's say R is a rectangle. Let's say the rectangle is, let's say, the open rectangle 0, 1 cross 3, 5. In R. So rectangle R2. So now we know that the area of R is going to be equal to 1 minus 0 into 5 minus 3, right? Which is equal to, that's the area of R. So let's denote it by mod R. So mod R is the area of R. Now let's take a density function f from R2 to R. R2 to R. What's happened to my stylus is gone off. Oh, it's coming back. Sorry about that. You guys get the screen or not? F2 to R, F of R2 to R, given by, I hope the screen is clear, given by, so what do? You say f of x comma y is equal to, so you say it's 1 by the area of R in the set when x and y are in R, and 0 otherwise. So that's how you define it. So this first thing is you define it. So you can clearly verify, it's a simple exercise to verify that f is a joint PDF. Okay, my pen is not working all of a sudden. Second. Let's see. I'm not sure what's going on. Let's come back. Very good. So F is the joint PDF. That's an easy exercise to check. Then one can also check the following, that for x and y with joint PDF F, the chance that x and y, let's say, is in some set A, let's say A is a set, let's say A comma B across C comma D, let's say in R2. Right? That's going to be just the integral from A to B and C to D f of x comma y dy dx, the whole thing divided by the length of R, which is just as a density function first. But what is this? Then suppose, let's assume for the time being that A comma B cross C comma D is contained in the set R, that is the rectangle R. So then this implies that, so if this happens, this implies that this is the same as the density is constant 1 over 2. So it's 1 over 2. And what's left is just B minus C into B minus C. So that's just the area of the set A comma B cross C comma D divided by the area of R. That's what that is. So this is so what is, if you think a little bit, what does this give you? This gives you a density function in a random variable that gives you the chance of picking a point x comma y in a rectangle A comma B cross C comma D is proportional to the area of the rectangle. So this is kind of the uniform random variable on the rectangle. So that motivates us to the following definition. Our first example of a dependent random variable is the following. So here's definition. Definition 5.4.4. Let D be a subset of R2. It keeps going up and down. Computer is freezing for some reason. I don't know why. Oh yeah, this is why. B is subset of R2. B non-empty with positive area. That is, D is a nice event. Then x comma y is uniform on D if the following happens. If it has a joint probability density function given by f from R2 to R, f of xy is equal to 1 divided by the area of D if x and y is in D and 0 otherwise. And where mod D denotes the area. So that's the idea. So that's this is a random variable that simulates this pair simulates the idea that you can choose a point uniformly in the set. So this is something that we write down. So this is like x and y. X and y choose a point uniformly in choose a point. That's what it's a random point uniform. So that's one. Right? This is one example. Another example, let me try. So this is an example. Another example, let me try and do is the following. Right. So the example 5.4.5. So here, let's say x and y have joint density f given by, so here let's say f of x comma y is equal to, let's say, x plus y, when 0 less than x less than 1, 0 less than y less than 1, and 0 otherwise. So now this is like one has to check now, is this really a joint density or not, before we sort of move on with this side. So the first step is, step one is f is clearly non-negative, right? F is clearly non-negative. So that's easy to observe, and it's continuous, because it's a linear function of x and y, and it's 0, piecewise continuous. Because it may have density, it's in the square it's continuous, and outside the unit square it's 0, so it's piecewise continuous. The next thing you have to check is, you have to check how the integral behaves, right? Integral from minus to infinity, f of x comma y. This has to be equal to 1. So what's that equal to now? That's the same as 0 to 1 of x plus y dx. So here I'm doing x first and y next. So this, if you step a little bit aside, so let me just do it in blue and red. So let's say x is blue, let's say, so x is blue, so 0 to 1 is in blue, and y is in red. So the first thing is that you have to look at this x. It's constant in x, so the image is right down in black. So it's 0 to 1, that's outside, that remains outside. In the inside one, you just keep the y fixed and integrate the x out. So you just get x squared by 2 plus y times x from the interval 0 to 1 dy. And that, if you finish off the integral, that's going to be equal to 0 to 1. This is just inside 1/2, and the other part is 0. And here you just get y times 1. That's all. dy. And that's now a one-dimensional integral. That's easy to do. That's just 1/2 times y plus y squared by 2 from 0 to 1. And that's just going to be 1/2 plus 1/2, and that's just. So we have verified indeed that the joint integral is equal to 1. So that's easy. Now let's just check if the random variable is indeed uniform or not. Right? So let's just do the simple thing. So let's say you want the interval a, the area a, set a to be, let's say, 0 to 1/2 cross 0 to 1. Let's say take that set. So if x and y were uniform, on the set 0, 1 cross 0, 1 on the unit square, then we know that the probability of x and y in A would be equal to the area of A divided by 1. And the area of A is just 1 point, right? If x and y are uniform. But let's check what x and y are. So the chance that x and y are in the set A, that's going to be what now? So it's going to be 0 to 1/2 in the x variable, or the y variable, let's say, and then 0 to 1/2 in the x variable. And I'll have f at the point x comma y. And then I have dx and dy. And that's going to be equal to 0 to 1/2, 0 to 1/2, and this is going to be, the density function is x plus y, right? So it's x plus y in the region, 0 to 1/2, and not, or in the interval 0, 1 cross 0, 1, so it's exactly. It's going to be equal to dx, and this is dy. So what's that going to be again? That's the same thing as saying we do the whole integration out. You will just get. So I'll leave this exercise. If you do this whole thing, you will just get 1/8. 1/8. So this is not the same as 1/4. So that means x and y are not uniform. Then one could also do a simple thing. One could do could say, fine, let me just, from this, let me see how X behaves. Can I just see how X behaves? So let's say, to understand behavior of X alone. Right. So can I do that? So how does one do that? From this joint density. So I'm given the joint density and I want to find the behavior of X. So how does one do that? So let's say X is an element in R. And we know that if I know the distribution function of X, then I know everything about X, right? Then I know everything about X. So let's try and calculate. Let's try and calculate distribution function of X. So how does one do that? So we have probability X is less than or equal to X. Now, it involves only X here, right? Only X here. Now, how do I bring in Y? But this is the same as X is in X and Y can be anything. So Y can be anything, I just put Y is in R. So Y is in R, same as minus infinity less than Y, less than. These two are the same because this is because why is this true? Because probability that Y is in R is equal to 1. So let me write that a little differently again as before. This is because probability of minus infinity less than Y less than infinity is equal to 1. That's why this is true. Is because probability of this event is 1. Red color, let me put red color here. That's just true. Now, but now you can go back. Now, this is the same as saying the probability that minus infinity less than X less than equal to X, minus infinity less than Y, less than infinity. So let me write the Y in red. So that way it's clear that I'm leaving the red out with Y. Sorry for that. So minus infinity less than Y less than infinity. So here it's minus infinity less than Y less than infinity. And that's going to be equal to, now we know how to do this because this is a integral, so it's minus infinity to X on the outside, then minus infinity to Y on the infinity on the inside. And I have F, let me write this in red, it's okay, F of this comma Y, dy, and then in black I have dx, right? That's our picture. But what is my density going to be look like? The density is going to be X plus Y only in the square, right? That means, so now in particular, first you observe, if X is less than 0, then this implies F of X comma Y is equal to 0 for all X, all Y. For all Y. So therefore, probability X less than equal to X is going to be equal to the integral of 0, which is going to be 0. Right? So let me write it down. Just copy this down. So it's going to be this. And inside the integral, I'll just put a 0 here. It's a 0. Because F is 0. So that means this is just 0. Now, if let's say, let's do second step. When X is between 0 and 1, then this implies F of xy is equal to X plus Y if Y is between 0 and 1, right? And 0 otherwise. If Y is in 0, 1 and 0 otherwise. That's what the definition of F looks like. Then we do the same thing, then therefore the probability of X less than equal to X in this case, and this is true, and in the region 0 less than X, otherwise it's 0. So then you just do a little bit of calculation, then you get the same thing, right? Just go here, do this, duplicate it, bring it down. This person here is going to be, so the F is 0 beyond negative side, so it's going to be just 0 to X on this side. And here, in the red side, I'll just have from 0 to 1, because that's where the function is X plus Y. And I'll have X plus the value Y. And I'll have a dy and a dx. So now what happens here? So if you do this, this is going to be equal to, let's say I made a mistake with this x and x, same x and x. Maybe this integrand and the limits have to be a little different. So let me just call this as, just for this case, let me just call this as, let me just call all these guys as A. So it's a little bit easier for us. Or maybe instead of doing that, let me undo it. Let me use the integrand as, let's say, as another variable. Let's call it as f of u. F of u, du, du, and du. That's okay. Let's just do that. So now that's going to be equal to what? That's going to be equal to. So in inside I have, outside I have 0 to x. Right? In the inside I have uy, right? So uy, we have uy, that's for the first term because y is a constant. U is a constant, this is not y, plus y squared by 2 from 0 to 1. So I close that, and I have a d. And that, if you work out, is going to be just integral 0 to x, and the inside is just u, right? This is u plus a half, and that, if you work out, is going to be equal to u squared by 2 plus u by 2 from 0 to x, and that's going to be equal to x squared by 2 plus x squared. That's the, is that correct? That's correct. Great. So now you can also check, it's an easy exercise to check that if x is bigger than 1, if x is bigger than 1, then the probability that x less than equal to x will just be equal to 1. That's an easy exercise to check. So now you've computed the distribution function of x. This. So this is one way. So from this, you can easily go and compute the joint density, the density function of x. The density function of x is equal to the derivative of the distribution function. That we know is 0 when x is not in 0 and 1. Inside 0 and 1, it's going to be just this is just 2x by 2, so it's just x, and this is going to be x plus 1. Right. So let me now see if I can get this split view again for you. So let's see the view and see if I made any mistakes. So one thing we did was that we had a different joint density function, x plus y this time. And I wanted to understand if it is actually uniform first. But we noticed that immediately it is not uniform because the chance of x and y in a set A was 1/8. Then we said, okay, fine, from this x and y, can I find the distribution function of x alone? And by integrating out the y out, we're able to find the distribution function of x, so x squared by 2. And that, if we differentiated, we got the density function of x. So we'll try and explore this in the second half. Let's stop here.